Okay, fifth root. Now we've got our table, and our table is going to be this. And you can figure, it's not going to be 1024 too much. It's not going to be 243 too much. More than likely, it's going to be 32 if we're going to be anything, right? So, the fifth root (64). Well, the largest number that will divide 64, that's a perfect fifth. Fifth is 32, with 2 left over. What's the largest number divisible by 5 before 7? 5. So that's a 5 with 2 left over. What about 16? 15 with how many left over? So the leftover is 2x squared y. That's what's left under the radical. Fifth root of 32 is, fifth root of x to the fifth is, fifth root of y to the 15th is y to the third. Now, when I look at a set of parentheses, I don't care what's on the inside. This is the fourth root of that set of parentheses to the 14th. I treat it as though it's an x. So I break it into two pieces, set of parentheses, set of parentheses. And if I had an x there instead of an x to the 14th, I'm looking for numbers which are divisible by 4, right? Because I'm looking for groups of 4. So if I'm looking at what is the largest number before 14 that 4 will divide? 12. And I've got 14 of them with 2 left over. So when I look at that problem, that's what I see. So then this becomes the fourth root of parentheses to the 12, the fourth root of parentheses squared, and I didn't check to see what your book does on this. I want to take it at face value. And what's the fourth root of parentheses to the 12th? And I did it again. Look at that. What would it be? Parentheses to the third. And the fourth root of parentheses squared. And now parentheses is x minus 2. The reason why I say that is that this guy can be reduced down. And you're going to say, well, what do I mean by that? I forgot that I was still videoing. And that is, if I look at the fourth root of parentheses squared, it's the same as parentheses to the 2/4 power, fractional power, which is the same as parentheses to the 1/2. So the equivalent answer is x minus 2 cubed, and not a fourth root, but a square root. And you're going to say, well, how did I notice that? Well, remember, this would be the power of the radicand is 2, the index is 4, and then 2 divided by 4, it reduces down. But like I said, I take it at face value and just stop right there. I wouldn't worry about the nuances until you got into your textbook and found out that, oh my God, how in the hell did they get that answer? And then you would bring it into class and ask me, and then I'll tell you. So I don't want you to worry about it. Now, here is where what I would do is, I notice there is 4 divides 20 evenly. X to the 4th divides x to the 7th. Z squared divides z to the 9th. So I'm going to lose that denominator. So what I'm going to do is reduce first. So this is the opposite of the cube root. 4 divides 20, that's going to be a 30. X to the 4th, x to the 7th, that's x to the 7 minus 4, which is 3. Z squared z to the 9th, that's going to be a z to the 7th, and there's no y's, y to the 5th. So the new radicand is 30 x cubed y to the 5th z to the 7th, with the denominator gone. So yeah, Sarah, you need to reduce it first. Makes your life easy. Easy peasy. Now I need to break this down. Now there isn't a cube. 1, 8, 27, none of them divide 30, so 30 is going to go in the leftover position. X cubed is a cube. Y to the 5th, well, has a cube in it. It's 3 with 2 left over. And z to the 7th, well, that would be a 6 and 1 left over. You see, that's why we did that first pre-homework yesterday. Because that's the biggest part of doing these problems, is breaking them apart or breaking them down. So this then becomes the cube root of x cubed, that's x. Cube root of y cubed, that's y. Cube root of z to the 6th, that's z squared, because I'm dividing all the exponents by 3. I hit the bar, that sets up my cube root, and leftover.
Does that become negative?
Ah, and I forgot the negative, didn't I? Thank you. And yes. I knocked myself a point. -1. -1 for me. -1. I should have done it in red, so for all the world to see. Now, if I look at this one, nothing reduces out. However, you notice the denominator is a perfect fourth. 4 divides 24, 4 divides 4. So this becomes the 4th root of 256 x to the 8th divided by the 4th root of y to the 24 z to the 4. Denominator, 4th root of y to the 24, y to the 6. 4 divides 24 6 times. 4 divides 4 once, z to the 1. And now I've got to break that stupid numerator down. Do I have to break it down? Ah, yoo-hoo! Guess what? 256 is a 4th, isn't it? And what do I raise to a power to get 256? 4. We'll take it. Let me get rid of this little thingy here. And then the 4th root of x to the 8th is x to the...
Is it second?
Yeah, second. Thank you, Dominique. You're part of my video forever. Well, at least I told until I redo it. Which, in this chapter, who knows what's going to happen. I give you a semi-blank schedule, so who knows what's going to happen. I don't. Okay, well, b over a squared times. Now you notice that b to the 25th is a perfect fifth, so I'll have the fifth root of b to the 25th, the fifth root of a to the 22nd. 5 does not divide 22nd evenly, so I keep track of this. b over a squared times, the denominator is b to the 5th, because 5 divides 25 5 times. The numerator can be broken apart. What is the largest number that 5 will divide before 22? 20. And then with 2 left over. b over a squared times b to the 5th, the fifth root of a to the 20th, 5 divides 24 times, so it's a to the 4th, and the fifth root of a squared. Now I can reduce this thing down. A squared divides a squared once, a to the 4th, a squared times. B divides b once, b to the 5th, b to the 4th times. So my final answer is going to be a squared, fifth root of a squared, all over b to the 4th. So notice how careful I worked that problem. Slowly and carefully. Okay.